My name is Luc Alberts. I am a postdoc in the BRU21 program. In this presentation, I will give a short overview of my project that I'm doing in collaboration with Neptune Energy, entitled Automatic Seismic Reconstruction of Missing Section. The oil and gas industry uses seismic data to look in the underground in their search for oil and gas. After they've acquired seismic data, they use the standard interpretation software where you can auto-track horizons and faults, but these often require a lot of manual editing, and to interpret an entire seismic survey takes a considerable amount of time. Therefore, several people have attempted to apply machine learning to the various tasks of a seismic interpretation project. Here you can see some examples of fault interpretation, horizons, seismic phases, and even salt domes. However, hardly anyone has looked at unconformities. Unconformities are very important. Here you see a field example of unconformity where these horizontal or more or less horizontal layers are overlapping some truncated layers. Basically means that these layers have been eroded and later been overlain by new deposits. Erosion is important because it means that at one point these lower rocks were buried at a larger depth, and therefore the porosities and other properties that affect an oil play are negatively affected. On seismic data, with the eyes, a human can easily see where many of the unconformities are. However, auto-tracking often fails because the character of the horizon is changing all the way, and therefore an interpretation of an unconformity can be even more time-consuming. To start off, we tried a well-tested convolutional neural network and use it directly on the seismic data. So we labeled the unconformity, here seen with green, versus the remaining data with red, and then trained the model and ran some predictions. Now the results weren't too good. The trained data was more or less okay, but at very low accuracy, and data that was never seen before was completely wrong. So this is a standard problem where you have very few positives and very many negatives. Now to overcome this, we were looking at a thing that was more or less in common for unconformities. As you've seen before, unconformities can manifest themselves in many different ways, but many share one property, and that is a transition in dip below and above the unconformity. So if you compute the difference in the orientation between the points below and the points above each point, you get the largest difference at the unconformity. So we develop a workflow where we use this feature together with the seismic data, and in addition we generate a lot of synthetic seismic data. We train our convolutional neural network and then hopefully are able to predict where the unconformities are and possibly even predict the different types of unconformities. This will give several benefits. We can automatically detect unconformities, which will simplify the workflow. We can save a lot of time and therewith also money. And we can classify it into different types of unconformities and hopefully say something about the amount of associated uplift. This work has been published as a paper that was recently presented at the EHEE Digital 2020. This concludes my presentation. Thank you for your attention.